Hi, in this video, we want to take a look at model complexity and generalization in supervised learning. All right, so the main two topics that we're going to talk about are overfitting and underfitting when we're doing supervised learning. All right, overfitting is where we overfit our data to our sample data. There will always be a difference between our sample data and the population we want to predict on. Now, there's that difference. If I'm picking up that difference and I'm doing it a lot, what's going to end up happening is we're going to have overfitting. And that is to say that the model is going to look more like the sample data than the population data that we want. Now, underfitting is where our model doesn't reach the full potential of our data. Now, we'll also talk about bias. So bias will happen when the predicted value is not equal to the conditional average of our predictor variables for the target variable. So like there'll be a difference. You'll see this happen like over time. So let's say I fit a model and I'm using that model for like 10 years. So over time, things are going to change just from time happening. And so that my model will have a bias that will be biased towards old previous values. Also, bias can happen. For example, let's say I'm doing a Bayesian statistics model, and I choose a poor prior that the expected values don't match up to what the true values I'm trying to model's average. And so there's going to be like a difference. And so there's a bias, so we'll be generating some error in the model. All right, so in the world of supervised learning, our chief endeavor is to build models that can predict on unseen data. So usually data that's going to be collected in the future, we're going to drop into our model, make a prediction, see what happens. That's typically what we do in supervised learning. We could also do inferential models, but here we're going to be focusing on the prediction point of view. It is possible we could also use supervised learning for controlling systems, but usually, like if we master the side of prediction, we can apply models to other situations. All right, so now in supervised learning, like watching out for like pitfalls is easier said than done. The level of complexity we introduce in our models often dictates how well these models will generalize to our fresh data points. As we dive deeper into this topic, we will understand that there's no free lunch in statistical learning. While all models inevitably overfit their training data to some extent, our aim is to remain our aim is to curate the most optimal model for scoring possible. All right, so something I want to emphasize is that all models overfit on their training data. Just take that as a hard, fast rule. The algorithm that you use to fit your models does its best to get the best fitting model possible. Well, it's only got the sample data to work with. So to get the best fitting model that the algorithm could give you, it's going to have to fit as well as it can to your sample data. Now, there will always be a difference between your sample data and your population that you're trying to make predictions on. And that difference is why we will always have overfitting. Some models will overfit than others. All right, so what we need to do, we need to understand what we're doing, understand how to evaluate what's going on, and make choices that protect ourselves from getting smacked in the face by overfit models. All right, overfitting and underfitting are challenges for our data scientists, and we have to navigate this every single time. You always have to be mindful of it. Now, realize that it's not a binary problem. It's not underfit, overfit, or perfect. It's not black and white. It's a spectrum. And so there's like a balancing aspect. And like honestly, at work, I've overfit models intentionally to make sure that certain aspects are achieved of the project. So I had one project where I needed to fit the model better on the extreme values. Well, how I was able to achieve that for my stakeholders and for my boss was honestly to overfit the model so that the middle range was overfit, but it was picking up the extremes, the extremely high and extremely low values of the target variable. So overfitting might actually be a tool to achieve our goals, but we need to take the point. We initially start out when we're building models, we take the point of view that we don't want to overfit at all. And then if we need to, we can relax things and expand out. And so our goal is to model on the target population, not on the sample set. But the sample set is all I've got to work with. There will always be a difference between our training data and the population we want to model. 100% guaranteed. So let's go ahead and start digging into this. We're going to use the house prices advanced regression techniques data set from Kaggle. Now, I've already gone through and done data prep on a previous video. And so I'm going to use the prepare data. So I've already applied Boxcox and Yo Johnson to the target variable and to several of the predictor variables. I've also done binning on the categorical and ordinal variables. All right, so first thing I'm going to do whenever I'm doing a project, I set up my workspace. So I'm going to tell R to only print out 5 significant digits. The larger the SciPin number, the more R avoids scientific notation. It won't be 100% successful on this one. And a warn of -1 is to suppress warnings to be printed out. I'm removing any artifacts from my workspace, so that way I don't have any interference in my code. And I'm going to be using piping in the tidyverse of R, so I'm using the Magritter package. All right, so now let's go ahead and load our data. So I've already gone through, I prepared my data. I know what's already in all the columns. I'm using the readr package. This is a pretty fast package. It's not as fast as other techniques I could be using, but it's usually faster than most techniques. It's faster than base R for loading data. One thing that will speed things up quite a bit is if I specify the type of columns I have. Also, I have the option of just omitting columns by, I think with this one, it's a hyphen. If I put in a hyphen to omit columns to be loaded, this will be very, very fast for pulling in data. And all right, so in this data set, we have a test set that there's no known target variables on that. And because this was part of a Kaggle competition, I went ahead and dropped all those from this. So here, so in this data set, how I have it prepared, if we know what the target variable value is, it's a train data set value. And if we don't know the target variable value, it's a test data set. All right. And the tidyverse has something called a tibble. Tibbles are advertised as working just like data frames. That's not 100% true. Some functions won't accept tibbles, or they do weird things with them, but everything is backwards compatible with a data frame, so I prefer to have a data frame. All right, so now model complexity. We have 3 sources of model complexity: the mathematical structure of our model, the number of predictor variables, and the number of parameters. So the mathematical structure, is just inherently like the first level of complexity. If I'm doing something that is a lot more mathematically, algorithmically more flexible, I'm more prone to overfitting. I'm also have the opportunity to fit more precisely to my data. That's good and bad, depending on what's going on. As a rule of thumb, the more data I have, the more rows of data I have, the more complex of a model I can have and not risk overfitting. Yeah, so something to worry about, if I have more flexible modeling, I can also fit to the noise of the data, the difference between sample and population. The more I can fit, the more flexible the model is. So we have to be mindful of that, have to consider that as we're doing our model building. The more rows of data I have, the less of a risk of overfitting I have throughout the board, as long as I have good data. But quantity of data is not superior to quality of data. Good quality data is more important than quantity of data. Keep that in mind. All right, now the more predictor variables I have, the more complicated my model is. And the more predictor variables I have, the more prone to overfitting I am. And so this can increase, the model's complexity. With greater complexity, the model has increased flexibility, but a higher propensity for overfitting. Now, also the number of parameters. So it's possible to reuse a predictor variable in the model structure. So for example, if I had one predictor variable and a target variable, and I did a degree 3 polynomial regression, then I'm using that one predictor variable 3 times. I've got 3 parameters connected to that one predictor variable and then an intercept. So here, the more parameters I have, the more prone to overfitting I am also. But also, with this increased flexibility, I might be able to pick up a pattern, a trend in my data that I wouldn't be able to without the additional parameters. We have to find that balance. We can think of the parameters as having like more knobs or dials to adjust to improve our model. Now, if we don't handle it right, though, we will overfit. And it sucks when you've overfit a model professionally because you have to own it and you have to deal with the consequences. All right, so model generalization talks about how well our model goes from sample to population. All right, so if my model generalizes well, then in the future, when my model makes a prediction, it's going to be pretty accurate. If I have poor generalization, then the predictions aren't going to be so, great. Yeah, so a model that generalizes well will capture the underlying patterns in the data without fitting to the noise. That is the difference between the sample and the population. Now, overfitting and underfitting. Overfitting occurs when the model learns the training data too closely. And so it picks up like noise and outliers and anomalies in there. And it will often show near perfect performance on the training data, but poor performance on new unseen data. Underfitting occurs when the model doesn't capture the underlying patterns that it could have picked up if I would have adjusted my model. Usually because the model is too simple. And so usually things will perform, underfit models will perform about equally well on the training and new data. And so what we're going to do, we're going to use the features of these descriptions of the training data and unseen data to detect, do I have overfitting? Between overfitting and underfitting, it's better to underfit. Why? Well, because you know what's coming. So notice that if I overfit, we're going to see like really good performance on the training data, but poor performance on new unseen data. All right, so if I see a difference between training statistic and validation statistic or test statistic, that's a sign of overfitting. Now, if I see that the performance on the training data is about equal to the performance on the validation set or the test set, then I know what's coming at me down the road. I know what's going to happen. If I overfit, and I launch that model, I put it into production, we're going to make predictions. And then when those predictions are made and then the actual result happens, we compare our predictions to what happens. And we'll see, oh crud, I have a horrible model on my hands. It's my fault. I have to deal with it. Now, that's with the overfitting. If I have an underfit model, well, what's going to happen? Well, so I built a model. It didn't perform as well as it could have, but, in data science, we never really know if we're doing things right until it's too late. But I built a model. Let's say I underfit the model. So my model could have been better off my data, but with underfitting, that training statistics and the validation statistics and the test statistics typically will be close to how things will actually pan out in the real scoring data. And so what'll happen is I know how accurate my model is going to be, and it was good enough for me to launch in production. It's probably going to be good enough down the road. And no one's going to really notice if you underfit your model. They might go, I wish it was better, but you're not going to be in a bad position trying to explain to stakeholders or your boss why things are lacking. With underfitting, we typically know how the model will perform in the future. So that's a huge advantage. So between underfitting and overfitting, underfitting is much better because I know what's going to happen. And since my statistics give me an idea what's going to happen, I launched that model into production. I would have put it into production if it wasn't good enough. And so I'm not in a bad position. But with overfitting, we expect gold and we get manure. Now, if we were talking on the street and this was not like a job related thing, I would not use the word manure. I'd use something more unprofessional, but I'll use the word manure here. All right, so we can be in serious problems professionally when a model does not meet expectations. And remember that overfitting and underfitting are not binary conditions. They fall on a continuum. All right, so now what I want to do, I want to go off the rails and do some overfitting. All right, what I'm going to do, I'm going to take a very small data set from my data, and I'm going to basically set it up so that I'm going to get a horribly overfit model. And this is to go off the rails to show you worst case scenario of what we absolutely would never want to do in real life. I haven't seen anybody do anything as bad as what I'm about to show you. All right, so I'm going to go through. I'm going to take unique values of data for the predictor variable, and I'm just going to take the first occurrence of some unique values of the predictor variable, specifically lot area. And then I'm going to get the highest polynomial regression model, highest degree polynomial regression model I can possibly build off of that very small data set. Then I'm going to check to see the train and validation statistics and just show you what's going on. And so now that this code I'm just going through, I am taking unique values. I take unique values in my predictor variable, and just taking the first occurrence of those unique values, and then I'm minimizing to just a few data points, a few of those, and I'm going to go through and I'm going to build a polynomial of degree 1, polynomial degree 2, polynomial degree 3, all the way up to, I think I put it down for 10. And then we're going to fit the model and we're going to check the statistics. All right, so here, I want you to look at, first and foremost, look at the training statistics. So here, this is degree 1, degree 2, 3, 4, 5, 6, all the way down to 10. Look at how the training statistics, the mean squared error, just keeps on getting smaller and smaller and smaller and smaller. So this is indicating that if I only look at the training statistics, this would be indicating that I have a really good model. Now, let's look at the test statistics. So the test data is the data that is the unseen data. I should have called it validation here, but test is okay. All right, so basically it's just unseen data. Notice how it's getting worse and worse and worse and worse as we go down. And so here we can see that by training statistic, the worst model is degree 1. By test statistic, the best model is degree 1. We can see that by the training statistic, the best model is degree 10, but the worst model by the test statistic is degree 10, completely switched. So, and this is a very artificially, I had to think about how to build such a bad model, but this really shows what's going on. Now, one of the reasons why we need to think about this, and I talk about training statistics a lot, is that in the situation that I have very little data, I might not have the opportunity to use unseen data. Imagine the case where I've got 10 data points because data is very hard to get. Maybe it's very expensive, very time consuming. I've got 10 data points and I need to build a model, and this is all I've got to work with. This happens in real life. Now, if you're working at Google, like I've talked to guys who are at Google that like if there's under 1 million data points, they don't even consider building a model. That's great to have that luxury. But if you need a lot of data to build a model, in my opinion, you're not much of a modeler. You need to be able to model in the tough situations to be a really great data scientist. And so we want to be able to model not just when I have 10 million rows of data, but when I have only a handful of data to work with. All right, so this is horribly going off the rails. Also, notice that the difference between the training and test statistics gets worse and worse as I overfit more and more. The more I overfit, the bigger the difference between the trained statistic and the test statistic. Now let's go ahead and visualize this. All right, so here, this model is completely, totally, and utterly off the rails. This is a degree 10 polynomial. Now, you can see in this region, it's gone way down, goes up. Now here it's actually going up and down. It's a degree 10 polynomial. And so I know that it's going to be doing some stuff like this. And so it's going up to the left and it's an even degree polynomial. And so it's going to be going up to the right in the extreme. And it's got stuff in the middle. If you go back to Calc 1 and study that. Now, I want to zoom in on a smaller region of the X and Y to show you more nuance what's going on. Because this, visually, this doesn't look too bad, but notice that, this is, lower than negative 3,500. There isn't even a data point close to this low. There's no points even close to this low. There's no points even close to this high. This is just crazy. Now, if I go here, I've zoomed in on the X and Y. So here we're going from 80 to a little bit less than 80, a little bit more than 110. So I'm capping it here and zooming in on the values. We can see that it looks like there is kind of a linear trend, not a great linear trend, a lot of dispersion about it, but this is some craziness that like the plot can't even handle like the value that this is actually going down and back up. This is that extreme dip. This is going up. This goes down. It goes up and then it goes down, and then it'll go back up again. And so we can see that this doesn't look like our data at all. This is completely, totally, and utterly off the rails. And so as the polynomial degree increases, the model fits the training data more closely, which results in a decreasing training mean squared error. However, the validation mean squared error starts to increase, and then we get overfitting. The model is fitting noise present in the training data and doesn't generalize at all to the validation data. Now, there's also another thing to consider about the bias and variance trade-off. All right, so idea of bias is that if I take some predictor variable values, there is a conditional average of the target variable. Now, that average is whatever it is. Whatever the average is, it is what it is. Our model, if it's unbiased, if for this particular value, if our model is unbiased for this situation, I plug in these predictor variables, the predicted value equals that target value average. Now, bias is when the model predicts something other than the average for the true population. And so, this can happen when our data shifts over time. This can happen if, let's say, I'm doing a Bayesian statistics and my priors are off from where they should be in terms of expected value. And so, like, when I include my data, the posterior will shift to be less biased, but doesn't always work out that way. Now, we've got bias is a reason why we would have error. Variance also. And so this is the error arising due to the model sensitivity to minor fluctuations. And a high variance suggests that the model may have like random noise in the training data, which leads to overfitting. And there's also something called irreducible error. And this is just inherent noise in the system. This error component is independent of the model and cannot be reduced no matter what we do. And so when I break down my total error, I can say that I've got bias, component, a variance component, and an irreducible error component. And so in some aspects of statistics, sometimes we will go ahead and alter our bias to decrease our variance, or maybe we'll increase our variance to try and reduce our bias, and we can balance that out. This tends to be more of a statistics concept than a machine learning concept, but this is something we need to be mindful of in case we need to invoke it. So if I have a fixed total error with a fixed irreducible error, then I could, potentially by adjusting my model, increasing variance could decrease the bias, and then increasing bias could decrease the variance for us. All right, so now let's talk about finding optimal degree for that polynomial regression model. What we're going to do, we're going to use cross-validation to estimate the best degree of a polynomial regression model. I have one predictor variable, a target variable, and I'm going to use powers of that predictor variable to get the best model I can. And so now I'm going to get some wonky stuff out of the code here. That's going to be because of some machine accuracy aspects. And frankly, using high degree polynomials is just a bad idea. So I'm overshooting this intentionally to drive home some points. All right, so the training mean squared error is going to decrease as the degree increases. But after a certain point, the validation mean squared error is going to get worse and worse after I reach the optimal point. And notice how the difference between the validation and training statistics give us insight to overfitting. And the models with degrees less than optimal are underfit, while models with degrees greater than optimal are overfit. And so I'm going to go through and I'm going to build different polynomial regression models up to degree 20. And I'm using tenfold cross-validation. And all this code is here for you to slug through if you want to. In the end, here's the table of what I get. So first and foremost, I want you to notice that here's the degree. Here I've got the training statistic. Notice how the training statistic decreases down to its minimum. Now, at this point, this 20, you can see that it actually shot back up. Theoretically speaking, this shouldn't happen. This is because computers are not perfectly accurate. If computers were perfectly accurate as like theoretical mathematics and statistics say they could be, then this would be smaller than 106. If the machine was perfectly accurate, theory shows us that that value would be the smallest, but it's not. So I kept that in there just so you could see like this difference. All right, so we can see that 19, a pretty high degree, gives us our minimum training statistic. But check this out. Check out the validation statistic that we get, 0.34, 0.35, 0.133, 0.131, 0.131, and so we can see that down to here, and there is some randomness aspect going on, but we can see that the validation statistic overall decreases, then it starts increasing, and we can see that it's completely going nuts. It just goes insane for the mean squared error. And so if I wanted to actually use a polynomial regression model, I would be going degree 5 while the training statistic would indicate degree 19. Now, for us, something that is important is to notice that the difference is very important for us, that we want this. When I look and I see a small difference between training statistic and validation statistic in real life, that's an indication that I'm not overfitting. As the difference between validation and training get bigger and bigger, I need to worry more about overfitting. So remember that when I'm doing my model fitting, I'm always balancing underfitting and overfitting. I'm trying to find that optimal sweet spot where my data gives me the most information possible and where I don't overshoot the mark and overfit. It's better to underfit than to overfit. And there is always a difference between our training data and our target population, 100% guaranteed. And overfitting, underfitting is not a yes, no situation, black and white. It is a continuum, a spectrum. So for your homework, I want you to take your data that you've already prepared, and I want you to split it into training and validation and build a simple linear regression model, and with just one predictor variable, and just compare performance metrics on those of your training statistic and your validation statistic. Then I want you to use cross-validation like I did to find what looks like the optimal degree for a polynomial regression model. Then on this next part, I want you to overfit your model. I want you to take all of your predictor variables. I want you to do feature engineering, polynomials. I want you to do interaction. I want you to do anything and everything you can think of to overfit your model. I want you to go off the rails and overfit a multiple linear regression model. I want you to do this intentionally so that you can see what it looks like when things go wrong. So that way, hopefully, you'll get a feel for what that looks like when you're on a real life project and you've made the mistake of overfitting. You'll spot it before you put the model in production. Now, after you get your multiple linear regression model, I want you to take a look at lasso and ridge regression. Lasso and ridge regressions, what they do is they actually modify the coefficients to protect us from overfitting. And so I want you to do a multiple linear regression, and then with the same predictor variable, same target variable, run lasso and ridge, and then compare the coefficients. And this way, I want you to just kind of see like how regularization helps protect us from overfitting our model. All right, well, that's all I've got for you. Life is short. Do math.